Okay, welcome back guys. If you recall, in the last lecture we had introduced MOS transistor, MOSFET. We qualitatively discussed about the working of the MOS transistor, how the channel gets pinched off and how the current saturates, why it behaves like a transistor and how it acts like a switch. It's an extension of the MOS capacitor with source and drain contacts, and we are discussing about N channel transistor with on a P type substrate, but the P channel transistor on an N type substrate can also be discussed with appropriate changes in the polarities. Anyways, so I had discussed, I had told you about the shape of the ID VD curves, the plots. We call them the output characteristics, and I told them that they initially are linear and then they saturate. So today we shall basically derive simple mathematical expression to to summarize those IDVD characteristics, and many other things which will take help of some small mathematics, simple mathematics. Most of these are borrowed from the MOS capacitor expressions only, so you will see the familiarity there. And let's part already because now in MOS transistor, and please remember that MOS transistor is a very vast topic. There are many advanced topics also associated with MOS transistor. It will be huge. So in this course we will restrict ourselves to some simple concepts. Okay, we will not go to very advanced concepts. So we shall try to list down what are the important topics in MOS transistor, MOSFET, that we are going to cover in the next few lectures. Okay, so we'll come to the slide and I'll show you what are the topics that we will go through. Okay, so let's come to the board here again. So these are let me come to the highlighter here, the laser pointer here. So these are essentially the topics, 4 topics that we will learn in MOS transistor thing. First thing is a current voltage relation, and by current voltage relation I mean this particular relation, this particular current voltage relation. We have already discussed the qualitative aspect. We will do the quantitative aspect. We will try to derive a mathematical expression for this particular IDVD, that's called current voltage relation. We will derive a mathematical expression which is based on something called gradual channel approximation, GCA. Okay, gradual channel approximation. The second thing we will learn is substrate bias and the effect of substrate bias on threshold voltage. What I mean by substrate bias is that you see this transistor here, there is a substrate bias option that is there. It's a contact, it's a terminal that is connected to the body. This is called the body of the device. So this is a P substrate. So you will have a terminal coming out of the P substrate. Typically this is shorted to the source and grounded. Okay, typically this is grounded. Okay, please remember that. So typically this is grounded. So what happens is that typically this is grounded, typically this is called VBS. This is the substrate voltage is typically grounded 0. Okay, this is essentially shorted here and then it's grounded. Okay, but it may not be grounded also. If it is not grounded, what is the effect of this threshold of this this substrate bias? This is called substrate bias, right? If you do not ground it, if you in fact apply some voltage to here, what will be the effect of substrate bias on the threshold voltage? How will the threshold voltage shift? So that part also we have to we'll take a look. That is the second point here. Okay, it's a very important point because you will see that you will be able to get more flexibility using substrate bias. So let me come back to the pointer again. So the second thing is the substrate bias and the effect of substrate bias on the threshold voltage. The third point is very critical and it's called subthreshold conduction and subthreshold slope. What it means is that before you turn on the channel completely, what I mean is that before you reach strong inversion, there is weak inversion and there is a small amount of conduction that you cannot actually observe in a linear scale. That's called subthreshold conduction. It happens when there is weak inversion before strong inversion has happened. So in a ID, VG characteristics, basically when your gate voltage is slightly below your threshold voltage, you will have a small conduction, that is called subthreshold conduction. It is very important because this will define your on off ratio, and how steep your slope is will tell you how how sharply you can turn on the device and off the device. Okay, and the fourth and the final thing is that we will discuss some short channel effects. This become prominent when your device becomes very small, which means your channel length becomes very small. Okay, by very small I mean less than 1 micron typically. but it can be even very highly scaled like 100 nanometer and so on. So, short channel effects have many things, out of which we will discuss 4. One is the scaling aspect. When you scale down the device, how does it affect the device performance? When I say scale down, you shrink down all the device dimensions. Remember, short channel effects come because the devices are basically made smaller and smaller, which means they are being scaled down, and this is following Moore's law that every 18 months your devices number will basically almost double. So, there will be more than density of devices that are packed per unit area. Your devices will become smaller, and that has effect on the short channel effects. You will have something called charge sharing between the source and the drain. When the the source and the drain are very far apart, what I mean is that if this is source, this is drain, this distance between the source and drain, this is the channel, okay, it's much larger, then you don't care about it. But when this channel becomes very small, the source and the drain depletion region approach each other, and then there will be some charge sharing that will affect the on and off state current of the device, the threshold voltage and other things. And dibble is drain induced barrier lowering. Punch through, this is basically again a phenomena that happens when your source and drain comes very close to each other, because your channel is very small or scaled down. Okay. And the final thing we will study is the channel length modulation. It is essentially not something very important compared to dibble, but we will still go through it nevertheless. Okay. So, the first thing that we will do today in this lecture is to derive the current voltage characteristics using the gradual channel approximation. Okay. What does the gradual channel approximation say? So, I told you at the beginning of last lecture that now it is a 2-dimensional picture where this your current is going to change, because you are applying a voltage here, you will have a potential variation along this direction, which we will assume to be linear, which means along this y direction there will be some voltage that is changing because of this, but the band bending is happening in this direction. If you remember from the MOS capacitor, I told you this is the x direction, for example, but so I can, the nomenclatures can vary. For example, I might call this as x to make it simpler, and this is y, that does not matter. So, in this direction, in this perpendicular direction, you will have a band bending here, you will have a channel that will form and a band bending over here. Okay. And in this direction, you will have a potential that you are applying here. So, there will be gradient of the potential over here. Now, the gradual channel approximation will tell you that the variation of potential in this direction matters actually, in this direction. The variation of potential along this direction can be ignored. Okay. The variation in this direction can be ignored, which means we can assume that the channel that is formed at an infinitesimally thin, like a layer here. So, there is no variation along this direction. Okay. And the potential varying along this direction of the channel where the current is flowing is what matters. The potential varying over here does not matter. This is the simple gradual channel approximation that will hold true for many of the long channel cases, and we can get expressions that are fairly accurate, although it will break down when your device becomes shorter, okay, and when your device pinches off, for example. Okay. So, what I will do is that if I take a small slice of material over here of thickness dx, okay, and remember this is the depletion, by the way. If I take a small slice of thickness here dx, then the differential resistance associated with that will be given by dx by the conductivity in a way. Okay. So, this is the charge q and x is the, what is qn? Qn is actually the inverted electron charge, which is a function of position x. This is I am calling as x now, this I am calling as x. Okay. As a function of x, your inversion charge will change, because I showed you at pinch off, eventually here your charge will become 0, it will be like a triangular profile. So, q1 of x is essentially the electron charge as a function of x. Then there is a mobility. I will assume that mobility is constant everywhere, although it may not be the case every time, and z is the width of the device. So, that does not matter so much, it is basically normalizing the current. So, essentially the differential resistance associated with this particular differential element dx is the dx, the element here divided by the conductivity, which is the resistance here. Okay. So, what are you doing? Why are you doing this? We are trying to do this to essentially derive the current versus the voltage that you are applying. Okay. Now, let us take a minute and look very carefully. The total charge in the semiconductor here, is called Q of S, Q semiconductor charge, which will also vary as a function of x. The total charge in the semiconductor is the inversion charge here plus the depletion charge here. There will be some depletion charge, right? You are also applying a voltage here. So, the depletion, you see the depletion width gradually increases to this side. This side, the depletion width is more than this side. Why? Because I am applying a positive voltage. So, the depletion is wider this side and then this side. Okay. So, the depletion charge also will be a function of x. So, depletion charge as a function of x plus the channel charge as a function of x will give you the total semiconductor charge as a function of x. Okay, till now it's clear. Okay. Now if you recall this expression from your MOS capacitor, the gate voltage that you apply, part of it drops on the semiconductor, which is this, part of it part of it drops on the oxide, which is this, part of it drops on the semiconductor, which is the band bending. Of course, at strong inversion this becomes 2 times the psi f, which is the EM minus EF. But in MOSFET we will only talk about transit, the channel is inverted already because the channel has to exist. If the channel doesn't exist, then there is no point discussing this. So essentially this will be like 2 times phi f already. So this is the voltage on the oxide, this is the voltage dropping in the semiconductor. This is the flat band voltage that you have to account for because your metal and semiconductor work functions are different, your oxide charges might be there. So this is the threshold voltage expression from the MOS capacitor, which you are very familiar with. Now you remember that the total charge in the semiconductor over here, this expression over here, is equal to the charge on the in the inversion channel and the charge on the depletion region. Now you juggle around here, you put this value over here, you put it there, and you do some mathematics here and there, you will get an expression for Qn of x, which is the charge mobile carriers, the charge of the mobile electrons, that is the inversion charge. This is the inversion charge. Remember the current voltage characteristics that I showed you here, this current is carried exclusively by the electrons that are formed here. Okay. So the inversion charge that has formed here, the electrons that have formed the inversion channel here are alone responsible for the current this. So we are interested in the electron charge, not in the depletion charge. Okay. That is why you are looking at the electron charge here. So this is the electron charge there, and that electron charge is a function of x because I told you along the channel the potential is going to vary. That is given by this expression, this VFB, this should be subscript, sorry, this should be VFB. Okay. So this is given by the capacity, this is basically the capacitance of the oxide, which is epsilon by d. This is the band bending on the surface, minus this is the gate voltage minus the flat band voltage, the whole thing is here, product is here, minus the depletion charge. Now what do you do? Remember that this band bending is essentially 2 times the phi f, which is the EM minus EF. Okay. This band bending that is happening on the semiconductor, this band bending is essentially 2 times the EM minus EF, plus there is a Vx here. Why? Because if you look at this, if only MOS capacitor was there, then yes, the band bending at this interface is equal to 2 times the phi f, okay, that you know. But because there is a drain voltage that you are applying, there is a voltage that is changing here, that voltage must be added here. At any point x, the voltage that you are applying here will be V of x. Eventually at this point voltage will be Vd, at this point voltage will be 0. So at any point here voltage will be Vx. That voltage Vx has to be added to the total band bending here, because you are applying. In MOS capacitor this was not there, no, now it is there. So you have to apply that voltage actually. So that is why you will have to apply that voltage Vx to the band bending that is happening. And the depletion charge, if you recall, the depletion charge that is formed here, this depletion charge is, if you recall the MOS capacitor lecture, it's square root of the thing, this expression that is there, except that instead of 2 phi f, which was there in the MOS capacitor, in MOS capacitor you only had this much, here instead of 2 phi f you have to add 2 phi f plus Vx, because this Vx is also being added to 2 phi f along the channel, right. This potential along this channel Vx is added to the band bending in this direction, right. So that is why it comes here, there is a bracket missing here, sorry about that. So this will come here. So this expression of the depletion charge you put here, and this expression you put here, you do some juggle around, and then you get this expression for Qn of x, which is the mobile electron charge in the channel, and this mobile electron channel charge is alone responsible for IDVD. So we are only interested in this charge. Okay. This is given by this huge looking expression, nothing very fancy, nothing very fearful. Now to get your current voltage, you basically take this expression into account, that the potential that is dropping across this differential small length dx is given by the, this is not id, this is actually, this should have been I superscript d. So let me correct this again right here, so that you do not have this problem here. So this looks like that. Okay, this looks like that. So you see your sorry, you have a, I will take the marker here, the laser pointer here. Okay. So essentially the voltage that is dropping across the voltage that is dropping across your differential element dx here will be equal to dV, which is equal to the current that is flowing. The current has to be continuous everywhere, ID, times the resistance here, right? And dr, if you recall from this previous expression over here, this is the dr, right? So you substitute that here, right? And this qn, essentially you take this qn you put it here, okay? And then your id, this expression if you put here, then it will be id times this expression dx. This can be taken the other side, so it will become like that. Now you integrate over this entire channel length from 0 to L, you will get the expression, this expression, okay? This is the expression for your final current as a function of voltage. Vd is there, Vg is there. Of course there will be something called theta. The theta is called the body factor, and this is again Na. So this Na is the doping concentration in a substrate, is given by the this particular quantity. This theta can be actually neglected, because if your doping is light in the substrate, Na is the doping in the substrate, if doping is light in the substrate, and your oxide is thin, because this is epsilon by d, so epsilon will be denominator, d will be here. So if d is here, if the oxide is thin, which means that d is small, this is large, and then if the doping is small, this is small, then this quantity will be very small, and this part sometimes can be simplified, okay? This part can be simplified. So that we will do it now. So you see, initially it is a linear, it will vary. After that there will be non-linear region, and once the channel pinches off, which means towards the gate end of the drain or drain end of the gate, your gate is like with respect to the drain, the gate is pinched off. So the number of electrons arriving at that point will be important, not the how fast they are swept away, if you recall in the last lecture. So that's why the current will saturate, okay? This is called the body factor. And in the linear regime, in this regime, your gate voltage, actually the drain voltage that you are applying is less than this particular expression, because you are applying a very small drain voltage here, and in that case you can simplify this expression. If your drain voltage is very small, then you can do some Taylor series expansion and you can do some simplification. What you will get, this Z is, by the way, like the width of the device. Some textbooks call it W also. This is the width of the device, okay, periphery of the device. So the current that is flowing in this regime, in the linear regime, in this regime especially, not even here, because here it will approaching non-linearity. Over here the current that is flowing is the width of the device by the length of the device. This is the channel length L. Mobility, Cox, mobility I am assuming to be same everywhere. Cox is basically the oxide capacitance. Vg minus Vt, this quantity Vg minus Vt is called the gate overdrive, okay? Always remember that Vg minus Vt is called the gate overdrive. So Vg minus Vt, so of course the gate voltage has to be more than threshold voltage. If your gate voltage is less than threshold voltage, then everything here will fail, because the channel will not be formed. The premise, the basic foundation is that the gate voltage is more than threshold voltage, only then your channel is formed, right? So your gate voltage is more than threshold voltage by some amount, so that amount is this times the drain voltage. So you see this current varies linearly the drain voltage. So if the drain voltage is in this regime, the current is varying linearly. That's what is happening. Also the current varies linearly with gate voltage. So if you step down the gate, these are different gates. If you take on fixed drain voltage, along with that you will see that the current is also changing along with the gate voltage, okay? So this quantity is very useful in understanding the linear regime. Then we will come to the highly nonlinear. I am not deriving the expression for here. Essentially, if your drain voltage is much higher, such that the current saturates there, then what will you do? Okay, then what will you do? So once you have the channel becomes pinched off, which means I will come back here. Once your channel becomes pinched off here, it was actually highlighted in this diagram. Yeah. So once your channel becomes pinched off here, this pinched off here, no, I told you the gate becomes negative with respect to the drain, so this particular region becomes pinched off. Once the gate becomes pinched off here, then your gradual channel approximation will no longer hold true, okay? Your gradual channel approximation will become invalid when the channel gets pinched off near the drain. Now ID will saturate at VD set, which means this is the VD set, right? This is the locus of VD set, by the way. For different VG, your VD set also goes. For example, this curve, this is the VD set. So this point will be VD set. For this curve, this is the VD set. So this point is the VD set. For this point, this is the VD set. So the location of VD set is basically, VD set is the voltage at which the current saturates. The current at the voltage at which the current saturates is called VD set, and that VD set depends. This is VD set here. This is VD set for this. This is the VD set itself moves position as your gate bias keeps increasing, okay? So your VD set, this point, right, or this point, essentially at that point the current saturates. Now what happens at the current saturates? I told you that your gate will become pinched off, which means the channel charge Qn, remember Qn is the channel charge as a function of x at x equal to L, which means at x equal to L means at this point L, at this point x equal to L, when your channel becomes pinched off, the current saturates, which means you get this kind of ID, this kind of profile here, right, saturated. So at x equal to L at this point, your total, your not total, your mobile electron charge will become 0 when your channel pinches off here. So what you do is that you put mobile electron charge x equal to this total electron mobile transition, the inversion charge as 0 at x equal to L, and at that point you will put V equal to Vd set where the current saturates. Okay, assume that the voltage drop oxide is very low compared to the band bending that is happening, so we can neglect this term in the Vth expression, and this theta, the body term, can be neglected because if the oxide is thin and the doping is low, then this quantity will become very small. Okay, so with this condition you can get a simplified expression of Vd sat as this. Okay, you will do some juggle around, you can get the Vd, you basically put here in this expression, in this expression you put this as 0, x equal to L, and this will basically be Vd set, then this 0 equal to this is Vd set, this is Vd set. So if you do some juggling around, what you will get is that this expression you will get, this is the Vd set expression you will get, which is almost equal to, if you do some Taylor series expansion, you will get Vg minus Vt. Actually this is Vt, threshold voltage, by the way. So you will get Vg minus Vt, assuming that the voltage drop on the oxide is negligible. Okay, so Vg minus Vt is basically the gate overdrive, and you plug that into expression for this particular expression, you plug it here, what will you get? You would do some simplification, you will get this. So the saturation current, which is this current, okay, please remember this is the saturation current, this not this. Okay, this is the saturation current. So saturation current depends as the W, the width of the device, mobility, oxide capacitance by 2 times the length. This is the gate overdrive whole square, Vg minus Vt whole square. It doesn't depend on drain voltage. You see, this current doesn't depend on the drain voltage, right. So the expression also shows you that the drain current saturation doesn't depend on the drain voltage, but it depends on the square of the gate voltage. Okay, the square of the gate voltage. So that is your basically expression for IV in saturation. Now remember, these are simplifications that are done with some assumptions, like for example the voltage dropping on the oxide is very negligible, the band bending is much higher in the voltage on the oxide, theta is less than 1, which means the doping is light, the oxide is thin. But if all these conditions are not met, for example the voltage in the oxide cannot be neglected, you know, the doping was not very light, the body factor cannot be neglected because the oxide was thicker. In all these cases you cannot have this simplified expressions like this. For example, you have to use this particular expression and plug exactly the different values. On this you have to plug the different values and you can get the IDVD. Okay, this is the Mader expression, this is the mega expression from which we are deriving things. Okay, from which we are deriving things. So please be advised that this is an important expression and all the simplified things are actually done from here. In some textbooks though, this particular expression that you see here in the linear regime, which is this, some textbooks also have a term here minus Vd by 2. What I am trying to say is that, let me actually, it depends on the simplification that you are doing. Actually it depends on the simplification that you are doing. So in, for example, if you do not, in this particular expression, some of the terms you might expand in some other way, some of the terms you might neglect. So different textbooks do some different kind of simplifications. So in some textbooks this expression in the linear regime here, this expression is slightly modified. Okay, just keep in mind this is ID equal to Z by L mu and Cox. Here what they do is that Vg minus Vth minus Vd by 2 they do into this Vd. Okay, so this expression is exactly the same except that there is a Vd by 2 term here, minus Vd by 2 term here, that can give you a little bit more accuracy, and this is more important when you go near this part, when you are approaching the nonlinear regime. Okay, close to 0 this is fine. Okay, so please remember that. Okay, so some of the textbooks also do that. Okay, So just nothing. If you recap once again, there's nothing actually very scary or fanciful about this. What we did is that we took a differential element on the channel. I told that the resistance associated with this differential element is basically given by this expression. This is the charge in the channel, this is the mobility, this is the width. Remember, the current is exclusively carried by the mobile charge Q and X. So, we are interested in this, we are not interested in the depletion charge. Okay, we are not interested in it, we are only interested in the channel charge, the Qn. Okay, I told you that the total semiconductor charge is equal to, and this is a function of x by the way, because along this direction x is varying, and because you are applying V potential here, at any point the potential is Vx. So, the x is varying along this direction. Okay, so total semiconductor charge is total depletion charge and the total charge in the inversion layer. We are only interested in this part. So, what we go ahead and do is that we recall the threshold voltage expression, we recall this expression which I have written just now, this expression just now, and we substitute one from in the other, and we get an expression for the total. This is the total channel charge, this is the total channel inversion channel charge. Okay, at strong inversion, assume the strong inversion is already there. Okay, there is no question if there is no inversion there. And this particular band bending that happens, if you remember, there's band bending that happens, this band bending that happens, whatever that band bending was actually 2 times phi f at strong inversion, but because there is also a linearly varying charge, this V of x, you are applying a drain voltage. This drain voltage was not there in MOS capacitor, but now it is there. So, you have to add that also at any point x, that also will become plus V of x, right. And so, that is why essentially this is there, this quantity. Similarly, the depletion charge was actually this quantity, but now because there is a V of x there, you have to also add that here. So, it becomes like that. You plug in this and this in this expression, and then you get this particular mega expression. Now, you do a small integration to find out the current. That current will basically be this expression. This current is expression. You can do some Taylor series expansion, some simplification to basically make it simpler looking. Anyways, with some simplification, you can get this expression for linear. I told you in some textbooks they have a Vd minus 2 term here. Okay, like this. So, you have a linear expression and an expression for saturation current that gives you this expression. Okay. So, with this we conclude the IV relationship, and in the next class we will study substrate bias and the effect of substrate bias on the threshold voltage. Okay. So, we are moving at good speed. So, let's we'll end the class here. We have discussed basically the difference between the linear and the saturation regime. We have also derived the expressions for the current for the linear and the saturation regime. These are approximation of the main expression that we had derived for the current. For various numericals, for very simple problems, we can try to solve some of the problems later in the course. We can use these expressions to find out the linear and the saturation current density. Okay. So, the current saturation MOSFET, that is very important, saturates when the gate end pinches off because you go to a higher drain voltage. That is what has happened. So, in the next class we will take into account the substrate effect, the effect of the substrate bias, how it affects the threshold voltage, and then we will go to subthreshold. We will go to short channel device, and we will finish MOS transistors. The next maybe 2, 3 or 3, 4 lectures. Okay. Thank you.